Alright, now we're starting chapter 9. And chapter 9 is all about sequences and series. Funny thing about chapter 9 was when I was in school, it was the bane of my existence. I did not like sequences and series. I don't know, for some reason they didn't quite mesh with me, but this chapter has become one of my favorite ones to teach, and I think one of the most useful ones in all of mathematics. So when we talk about sequences, sequences are the little brother of series. All we're doing in the sequence is we're just figuring out what terms they are. A series, we're going to take all the terms and add them together, but a sequence is just really all the terms. So if we know a sub n is 2 to the n minus 1, we want the first three terms in the sequence, you get two questions. You don't know exactly what n starts with. We're going to take n to start with at 1 unless told otherwise. You look down here in number 4, this notation tells us what n starts at. N starting at 0. So if we don't see anything, we're going to take n to be 1. So we really just have to plug it in. So it's 2 to the 1 minus 1, or 2 to the 0, which is 1. And then we do 2 to the 2 minus 1, which is 2 to the 0, or 2 to the 1, or 2. And then our third one is 2 to the 3 minus 1, or 2 squared, 4. And then when we're just writing down our three terms in our sequence, we're just writing 1, 2, 4. That's really it. So for the next one, we just plug in 1. 1 squared is 1, minus 4 over 1 cubed, which is 1, plus 1. That would be our first term. And then our second term, we plug in 2, we get 4 minus 8 over 2 cubed, which is 8, plus 1, which is 9, so on and so forth. 9 minus 12 over 27 plus 1. Simplify, see what you get for each term, and that's it. The notation at the bottom here is saying we're doing this series from, or sequence, sorry. You may find me saying one term and meaning the other many a time in this chapter. So since we're doing sequences, we're not adding them together. So this is starting with 0 and going to infinity in general. We just want the first three though. So we have negative 1 to the 0 plus 1 over 2 to the 0, which is 1. Now this negative 1 to some power comes up a lot in this chapter. And really all it's going to be is it's going to alternate. And when it's even as an exponent, it's going to be positive. When it's odd as an exponent, it's going to be negative. So I can expect that each of these terms is either going to be negative 1 or positive 1. Well, the first term comes out to being negative 1. Sorry, I mean equal. And the next one's going to be a positive 1 over, well, as we see up here, 2 to some power is really just 2 times 2 times 2. So times 2 is 2, and the next one's going to be a negative 1 on top to the fourth on the bottom. So the next one, without even looking at the original formula, is going to be a positive over 8, and then a negative over 16, positive over 32, etc., etc. Oh, going too far. Oh, come on. This thing's giving me a little bit of trouble here. Alright, so we got a couple theorems here. Limit of a sequence is really saying that if you take the limit of a sub n and you get really a number, limit of a sequence, it's really end up telling you that you can treat the sequence like a function. So if you can find that f of x equals a sub n for any number n. Now, a sequence doesn't really go like a function. A function I expect to be continuous. I expect that you can plug in 1.1, 1.2, 1.3. But if we just treat them as far as the integers are concerned, not really the integers, even just the whole numbers are concerned, it still works the same. So the limit of the sequence, if I can figure out some function to kind of take the place of the sequence, it's the same thing as the limit of f of x as x goes to infinity. So it's not anything new. It's really exactly the same thing. So the good news is you can treat a limit of a sequence just like you treat the limit of a function. So if the limit of this f of x equals some number, It's the same as the limit of a sub n equals the number. It doesn't matter that it's not continuous. It doesn't matter that it's every term individual. Squeeze theorem is kind of a tricky one. You don't use it very often, but it basically says that if you've got some a sub n, which is smaller than b sub n, which is smaller than c sub n, and the limit of a sub n equals the limit of c sub n, that also tells us that the limit here, and we'll say that they equal k. That would imply that the limit of b sub n, the one that's in the middle, will also equal k. So what that looks like, the squeeze theorem is kind of cool as a picture. If you've got some a sub n coming around down here, and it approaches some limit here, k, and you've got b sub n that does something, but it approaches that same limit, or sorry, c sub n. So this is our a sub n, this is our c sub n, and you got b sub n bouncing around in the middle here somewhere. It also has to reach that same value. So it's a squeeze theorem. You think it's getting squeezed between two different functions. If they both approach the same value, then b sub n must also approach that value. It's kind of a tricky one to actually use. I mean, you see it used every once in a while in theorems, but it's not all that important for most of what we do.